Welcome to this session on absorption and stripping. Absorption is a vapor liquid separation technique that involves the removal of a material or a component in a multi-component stream by contacting the vapor stream with a solvent, right, in which the material of interest is soluble or interacts with. And if done right, we're able to remove um, most of the material from the vapor stream. And it's a fairly popular unit operation, very important one. It's used in a lot of applications to remove contaminants from a vapor stream, or in certain cases where the material of interest in a vapor stream, along with other things we might not be interested in. Absorption is a fairly common technique for that purpose. It's used for sweetening, carbon capturing, you know. So we're going to model that process using Aspen Plus. And remember, we spoke about radfrac, and we used radfrac for distillation. And how we said it was also capable, the model was capable or built for absorption as well. So we're going to do something similar in Aspen Plus and attempt to solve a problem using the absorber model in the software. So over here we have a problem. Example 2 is an IGCC power plant that generates some amount of electricity. So the key parts of this is some reaction goes on the gasification, and the products of the gasifier, it is desired to remove the carbon dioxide in the stream. It's one of the components in the stream, and it's desired to remove it using triethylene glycol and water, a mixture of that. So this forms our solvent or liquid phase, right? And the gas of interest is CO2, but it's in a multi-component stream consisting mainly of hydrogen and the carbon dioxide. So we're going to solve this problem using Aspen Plus based on the flow sheet. Our feed gas consists of hydrogen, should be water, and there should be triethylene glycol founded. So we add that. Specify the pipetting method. Choose to use Pen Robinson. And quickly we can move to specify a flow sheet. Okay, draw a flow sheet. So again, come to columns, radfrac. Any of these could be the absorber. Just use this. So it's very important to take note of the configuration of most of these equipment. Right? An absorber should have a vapor outlet and a liquid outlet, and it has two inlet streams, one for the solvent and one for the vapor phase. Right? We'll go ahead and put our vapor phase conditions. 110 Fahrenheit. That should be it for my feed stream, vapor stream. And I go on to the liquid solvent specification. And that should be it for solvent column. So maybe I should label my streams, rename them nicely. Solvent. So, for this problem, we use a 14 stage absorber. The way you know it's an absorber is turn off the condenser and reboilers. Then Aspen knows this is an absorber. So we change the conversions criteria to petroleum white oil. And that should be it, the configuration. So you go to the streams, and this is very important in simulating absorption columns. Many a time, the the mistake most people make is the poor by wrong allocation of the streams, right? So if you have a vapor stream, you should clearly feed it at the bottom, and then the liquid should come from the top, right? So if you change these, your simulation might will fail to converge. You'd have errors like a number of stages drying up and having no liquid on certain stages. It's usually because of this mistake. So we go back to our flow sheet. The solvent should be on stage 1, counting from the top. So it should be on stage 1. Then this should be on stage 14, the gas. So put that on stage 14, and that should be it. Go to the specify the pressure. Looks like we are good to go. Should be able to run it. Have some results. Let's go and see what's happening in there. So we can look at the phases and the conditions. And the interesting part is to check the flow. So this is the, let me change this to pound so we can compare that. So we've recovered most of our CO2. We've been able to remove most of it, about 70% of the CO2. We could also check the temperature and composition profiles. It's just one of those. Composition is fine. CO2. Maybe not the most useful. What's this right there? One face. Just check the data. Maybe we should just customize. So come here. This is what's on. Selection. Hydrogen and CO2. Yes. And it's the behavior is as expected. Now stripping. Stripping is the opposite of absorption. Absorption, right? So here we use a gas, preferably a hot gas, usually hot gas, to recover components from a liquid stream. So it's usually done to regenerate solvents. If some of these solvents are expensive, and if used, in our case, the glycol solution to recover to remove the CO2, right? We might want to reuse that solution. So what we can do is we can strip the solution of the carbon dioxide and then return it back down the column. In some cases, if the CO2 is the material of interest, then we would want to separate it from the solvent, right, to recover it from the solvent, the liquid phase. So in that case, we do stripping. It's almost the same as an absorption column. It just operates differently. The configuration is just different. That is one way it is done. It could also be operated as a distillation column. It's in a similar fashion. So if we go back to our problem, our flow sheet, we had a stripper, right? So we are just going to modify the flow sheet to include the stripper. First we heat. Note here that our top stage is a vapor stream. So our flow sheet should also be as such. Streams connected to the top. The pressure is 150. That should be enough. And head to the stream results. And here we can quickly see the solvent phase. The solvent stream is one. CO2, almost none. So all of it has been removed. So that should be it for absorption and stripping. There's there are many more examples in the material that will be made available in the description. We see you at extraction. Thank you.